Chapter 1 Patterns in Mathematics Question Answers. Figure it out, page 2, question 1. Can you think of other examples where mathematics help us in our everyday lives? Answer. Uses of mathematics in everyday life. Cooking. When we measure ingredients to cook a recipe, we use math to ensure the quantities are correct. Second, shopping. Calculating the total cost of items and figuring out discounts involves basic math. Third, traveling. We use maths to determine distances, travel time, and fuel usage. Next, sports. Keeping track of scores, calculating averages, and determining player statistics all involve math. Next, banking. Simple mathematics is used when managing money, such as saving, spending, and calculating interest. Question 2. How has mathematics helped propel humanity forward? You might think of examples involving carrying out scientific experiments, running our economy and democracy, building bridges, houses, or other complex structures, making TVs, mobile phones, computers, bicycles, trains, cars, planes, calendars, clocks, etc. Answer. How mathematics has helped humanity. First, building structures. Engineers use math to design and construct buildings, bridges, and other structures to ensure they are safe and stable. Next, technology development. Math is crucial in creating and improving technologies like computers, mobile phones, and TVs. Next, scientific research. Mathematics helps scientists conduct experiments, analyze data, and make predictions. Next, running economies. Economists use math to model economic systems, forecast trends, and manage financial markets. Next, space exploration. Math enables us to calculate the trajectories needed to send satellites and spacecraft into orbit and beyond. Page 3. Figure it out. Question 1. Can you recognize the pattern in each of the sequences in table 1? Answer. Recognizing the patterns in sequences. All ones sequence 1 1 1 1. This one. Each number in the sequence is always 1. Second, counting numbers 1 2 3 4. Each number increases by 1. This one. Third, odd numbers 1 3 5 7. Each number increases by 2 starting from 1. This one. Next, even numbers 2 4 6 8. Each number increases by 2 starting from 2. This one. Next, triangular numbers 1 3 6 10. The difference between consecutive numbers increases by 1 each time. This one. Next, squares 1 4 9 16. Each number is the square of a natural number. Example 1 square, 2 square, 3 square, and so on. This one. Next, cubes 1 8 27 64. Each number is the cube of a natural number. Example 1 cube, 2 cube, 3 cube. This one. Question 2. Rewrite each sequence of table 1 in your notebook along with the next 3 numbers in each sequence. After each sequence, write in your own words what is the rule for forming the numbers in the sequence. Answer. Extending sequences in table 1. First, all ones sequence. The next 3 numbers are 1 1 1. The rule is that every number in the sequence is 1. Second, counting numbers sequence. The next 3 numbers are 8 9 10. The rule is to add 1 to the previous number. Third, odd numbers sequence. The next 3 numbers are 15, 17, 19. The rule is to add 2 to the previous number. Fourth, even numbers sequence. The next 3 numbers are 16, 18, 20. The rule is to add 2 to the previous number. Fifth, triangular numbers sequence. The next 3 numbers are 36, 45, 55. The rule is to add the next counting number to the previous triangular number. Example 1 plus 2 is equal to 3, 3 plus 3 is equal to 6, 6 plus 4 is equal to 10, and so on. Next, squares sequence. The next 3 numbers are 64, 81, 100. The rule is to square the next counting number. Example 8 square is equal to 64, 9 square is equal to 81, and 10 squares is equal to 100. Next, cubes sequence. The next 3 numbers are 125, 216, 343. The rule is to cube the next counting number. Example 5 cube is equals to 125, 6 cube is equals to 216, 7 cube is equals to 343. Figure it out, page 5. Copy the pictorial representations of the number sequences in table 2 in your notebook and draw the next picture for each sequence. So friends, I have already solved this question in the previous video. You can check the link of the video in the description. Question 2. Why are 1, 3, 6, 10, 15 called triangular numbers? Why are 1, 4, 9, 16, 25 called square numbers or squares? Why are 1, 8, 27, 64, 125 called cubes? Answer. Triangular numbers 1, 3, 6, 10, 15 are called so because they can be represented by dots arranged in the shape of a triangle. For example, 3 dots form a triangle with 2 at the bottom and 1 at the top. Square numbers 1, 4, 9, 16, 25 are called squares because they can be arranged in a square grid like 4 dots forming a 2 by 2 square. Cubes 1, 8, 27, 64, 125 represented the number of small cubes that fit into a larger cube, with each number being the cube of an integer like 3 multiplied by 3 multiplied by 3 for 27. Question 3. You will have noticed that 36 is both a triangular number and a square number. That is, 36 dots can be arranged perfectly both in a triangle and in a square. Make pictures in your notebook illustrating this. This shows that the same number can be represented differently and play different roles depending on the context. Try representing some other numbers pictorially in different ways. Answer. The arrangement of 36 dots both in a triangle and in a square. So friends, this is 36 dots in a square and this is 36 dots in a triangle. The same numbers represented differently as follows. Number 6. Triangular number. Arrange 6 dots in a triangle with rows of 1, 2 and 3 dots like this one. Next, rectangular number. Arrange 6 dots in a 2 multiplied by 3 rectangle. This one. Next, number 10. Triangular number. Arrange 10 dots in a triangle with rows of 1, 2, 3 and 4 dots like a pyramid. This one. Next, rectangular number. Arrange 10 dots in a 2 multiplied by 5 grid forming a rectangle. This one. Question 4. What would you call the following sequence of numbers? That's right. They are called hexagonal numbers. Draw these in your notebook. What is the next number in the sequence? Answer. So friends, these are the hexagonal numbers 1, 7, 19, 37 and the next number in the sequence is 61. You can draw this hexagon in your notebook. Question 5. Can you think of pictorial ways to visualize the sequence of powers of 2, powers of 3? Here is one possible way of thinking about powers of 2. So friends, as you can see 1, 2, 4, 8 and 16. Now let's see the possible ways of thinking about powers of 3. 1, 3, 9, 27, 81. So this is 3 to the power 1, 3 to the power 2, 3 to the power 3, 3 to the power 4. Figure it out, page 6. 1 is equals to 1, 1 plus 3 is equals to 4, 1 plus 3 plus 5 is equals to 9, 1 plus 3 plus 5 plus 7 is equals to 16, 1 plus 3 plus 5 plus 7 plus 9 is equals to 25, 1 plus 3 plus 5 plus 7 plus 9 plus 11 is equals to 36. Why does this happen? Do you think it will happen forever? Answer. This happens because adding consecutive odd numbers 1, 3, 5, 7 always results in square numbers. This pattern occurs because the sum of these odd numbers fills up a square grid, building the next larger square each time. Yes, this pattern will continue forever, as each new odd number completes the next layer of dots around the square. Next, how can we partition the dots in a square? Grid into odd numbers of dots 1, 3, 5, 7. Answer. We can partition the dots by starting with a single dot for 1, then adding 3 dots to form a 2 by 2 square, then adding 5 more dots to form a 3 by 3 square and so on. Each layer of added dots is an odd number, creating progressively larger squares. Page 7. By drawing a similar picture, can you say what is the sum of the first 10 odd numbers? Answer: sum of the first 10 odd numbers. By drawing a similar picture for the first 10 odd numbers 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, I would create a 10 by 10 square, this one. The sum of the first 10 odd numbers is therefore the area of this square, which is 10 multiplied by 10 is equals to 100. Now, by imagining a similar picture or by drawing it partially as needed, can you say what is the sum of the first 100 odd numbers? Answer: by imagining a similar pattern, the sum of the first 100 odd numbers would create a 100 by 100 square. Thus, the sum is 100 multiplied by 100 is equals to 10,000. This pattern holds true for any number of consecutive odd numbers, where the sum of the first n odd numbers is always n square. Page 8. Can you find a similar pictorial explanation? Answer: pictorial explanation. Imagine each number in the sequence as a row of dots. For example, 1 is equals to 1 dot, 1 plus 2 plus 1 is equals to 4 dots arranged as a 2 multiplied by 2 square, 1 plus 2 plus 3 plus 2 plus 1 is equals to 9 dots arranged as a 3 multiplied by 3 square, 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1 is equal to 16 dots arranged as a 4 multiplied by 4 square. The dots are arranged symmetrically around the central line, which corresponds to the middle number in the sequence. So friends, this is 1 dot, this is 2 by 2, this is 3 by 3 and this is 4 by 4. Figure it out, page 8. Question 1. Can you find a similar pictorial explanation for why adding counting numbers up and down, that is 1, 1 plus 2 plus 1, 1 plus 2 plus 3 plus 2 plus 1 gives square numbers? Answer: pictorial explanation for adding counting numbers up and down to get square numbers. The idea is to visualize each term in the sequence as rows of dots where the sum 1 plus 2 plus 3 plus 2 plus 1 can be arranged as a perfect square. For example, 1 plus 2 plus 1 forms a 2 multiplied by 2 square, 1 plus 2 plus 3 plus 2 plus 1 forms a 3 multiplied by 3 square, and so on. Each layer of dots forms the next square by adding a symmetrical layer of dots around the existing square. Question 2. By imagining a large version of your picture or drawing it partially as needed, can you see what will be the value of 1 plus 2 plus 3 plus up to plus 99 plus 100 plus 99 plus up to 3 plus 2 plus 1? Answer: sum of 1 plus 2 plus 3 plus up to 99 plus 100 plus 99 plus up to 3 plus 2 plus 1. This sequence will form a large square with side length 100, resulting in a sum of 100 multiplied by 100 is equals to 10,000. This pattern holds because the symmetrical arrangement builds a square with the largest number 100 as its side length. Question 3. Which sequence do you get when you start to add the all ones sequence up? What sequence do you get when you add the all ones sequence up and down? Answer: sequence when adding the all ones sequence up and up down. When I add the all ones sequence up, I get a sequence of counting number 1, 2, 3, 4 and so on. When I add the all ones sequences up and down, I again get a sequence of counting numbers but mirrored around a peak 1, 2, 3, 2, 1, forming a diamond shape. Question 4. Which sequence do you get when you start to add the counting numbers up? Can you give a smaller pictorial explanation? Answer: sequence when adding the counting number up, this one. Adding the counting numbers up gives triangular numbers 1, 3, 6, 10, 15. 1, 3, 6, 10, 15. Pictorially, we can visualize each sum as a triangle of dots where each layer has one more dot than the previous layer. Question 5. What happens when you add up pairs of consecutive triangular numbers? That is, take 1 plus 3, 3 plus 6, 6 plus 10, 10 plus 15. Which sequence do you get? Why? Can you explain it with a picture? Answer: sequence when adding pairs of consecutive triangular numbers like this, then this and this and this. When I add pairs of consecutive triangular numbers, example 1 plus 3 is equals to 4, 3 plus 6 is equals to 9, 6 plus 10 is equals to 16, I get square numbers 4, 9, 16 and so on. This happens because each pair of triangular numbers combines to form a perfect square, and I can represent this pictorially by rearranging the dots of two triangular numbers into a square. Like here, so this is 4, this is 9, this is 16, this is 25. Question 6. What happens when you start to add up powers of 2 starting with 1, that is, take 1, 1 plus 2, 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8 and so on. Now add 1 to each of these numbers. What numbers do you get? Why does this happen? Answer. Adding up powers of 2 starting with 1 and then adding 1. So the figure is this. When we add up powers of 2, example 1, 1 plus 2 is equals to 3, 1 plus 2 plus 4 is equals to 7, 1 plus 2 plus 4 plus 8 is equals to 15, and then add 1 to each sum, we get the sequence 2, 4, 8, 16, which are powers of 2 again. This happens because adding the sequence of powers of 2 up to a certain point and then adding 1 results in the next power of 2. This pattern can be visualized by pictorially doubling the size of a block of dots each time, like 1, then 2, then 4, then 8 and last 16. Question 7. What happens when you multiply the triangular numbers by 6 and add 1? Which sequence do you get? Can you explain it with a picture? Answer. When we multiply triangular numbers by 6 and add 1, we get hexagonal numbers. The sequence is 7, 19, 37, 61, 91, 127 and so on. This is the pictorial representation. This sequence forms hexagons when visualized, like 1, 7, 19, 37. This is the shape of a hexagon. For example, 7 represents a hexagon with one dot. This one. 7 represents a hexagon with one dot at the center and 6 surrounding dots. This is the one dot at the center and 6 surrounding dots. Each subsequent number adds another layer to the hexagon, maintaining its shape while increasing its size. This pattern visualizes the hexagonal structure. So friends, now this becomes the center here in 19 and we get another hexagon. Then this becomes the center in 37 and we get another hexagon. Question 8. What happens when you start to add up hexagonal numbers, that is, take 1, 1 plus 7, 1 plus 7 plus 19, 1 plus 7 plus 19 plus 37. Which sequence do you get? Can you explain it using a picture of a cube? Answer. When we start to add up hexagonal numbers in the sequence 1, 1 plus 7, 1 plus 7 plus 19, 1 plus 7 plus 19 plus 37, the resulting sequence is cubic numbers 1, 8, 27, 64. Explanation using the cube picture. These are the cubes. Each step adds another hexagonal layer to the structure. The first sum 1 represents a single cube, this one. Adding the next hexagon 7 forms a larger 2 multiplied by 2 multiplied by 2 cube, total 8 cubes, this one. Next, continuing this process forms even larger cubes, matching the cubic numbers 3 cube is equals to 27, this one, 4 cube is equals to 64, this one, etc. and 5 cube is equals to 125. The cube visualization shows how stacking hexagonal layers builds up a three-dimensional cube, each step adding a new complete layer that increases the cube size uniformly. Question 9. Find your own patterns or relations in and among the sequences in table 1. Can you explain why they happen with a picture or otherwise? Answer. Pattern. Connection between square numbers and odd numbers. Sequence of square numbers 1, 4, 9, 16, 25, 36. Sequence of odd numbers 1, 3, 5, 7, 9, 11. Relation. Each square number is the sum of the first n odd numbers. For example, 1 is equals to 1, 4 is equals to 1 plus 3, 9 is equals to 1 plus 3 plus 5, 16 is equals to 1 plus 3 plus 5 plus 7. Explanation with a picture. If we imagine forming a square by placing dots, start with one dot, then add a row of 3 dots to form a 2 by 2 square. Then add a row of 5 dots to make a 3 by 3 square and so on. This shows that each square is built by adding the next odd number of dots, demonstrating why square numbers are the sum of consecutive odd numbers. This pattern occurs because each new square is formed by extending the previous square by an L-shaped layer of dots, where the number of dots in the layer equals the next odd number. Figure it out, page 11. Question 1. Can you recognize the pattern in each of the sequences in table 3? Answer. Complete graphs. Pattern. Each shape shows points, dots connected by lines. These are the dots in red. Every point is connected to every other point and the number of lines increases as more points are added. Like in K3 there are 3 dots, so number of lines has increased. In K4 there are 4 dots, so number of lines are increased, and so on. Next, stacked squares pattern. Each shape in the sequence forms a square by adding more rows and columns of dots. The squares get bigger with more dots, starting with 1 dot, then 4 dots in a 2 by 2 square, then 9 dots in a 3 by 3 square, and so on. Next, stacked triangles pattern. Each shape in the sequence adds a new row of dots to form a triangle. The number of dots increases as you go down the sequence, starting with 1 dot, then 3 dots, then 6 dots, and so on. Next, Koch snowflake pattern. Each shape gets more complicated by adding tiny bumps to each side of the previous shape. This makes the shape look more and more like a snowflake as I go down the sequence. Question 2. Try and redraw each sequence in table 3 in your notebook. Can you draw the next shape in each sequence? Why or why not? After each sequence, describe in your own words what is the rule or pattern for forming the shapes in the sequence. So friends, in the previous question we have already discussed the pattern. Now let's see the next picture in the sequence. First, complete graphs. K7 is this one. In K6 we have 6 dots. In K7 we have 7 dots. Next, stacked squares. We have here 2 by 2, 3 by 3, 4 by 4, 5 by 5, and 6 by 6. So this is the next figure. Stacked triangles. So this is the next figure. Koch snowflake. This is the next figure. Figure it out, page 11, question 1. Count the number of sides in each shape in the sequence of regular polygons. Which number sequence do you get? What about the number of corners in each shape in the sequence of regular polygons? Do you get the same number sequence? Can you explain why this happens? So friends, these are the regular polygons: triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon. Answer: in the sequence of regular polygons, the number of sides is equal to the number of corners or vertices because each corner corresponds to a side. Here's the count for each shape. Triangle, 3 sides, 3 corners. So 3 sides and 3 corners. Next, quadrilateral square, 4 sides, 4 corners. So 4 sides and 4 corners. Next, pentagon, 5 sides, 5 corners. Hexagon, 6 sides, 6 corners. Heptagon, 7 sides, 7 corners. Octagon, 8 sides, 8 corners. Nonagon, 9 sides, 9 corners. Decagon, 10 sides, 10 corners. Number sequence for both sides and corners: 3, 4, 5, 6, 7, 8, 9, 10. The sequence is the counting number starting from 3. This happens because regular polygons have an equal number of sides and corners by definition, and as we move to polygons with more sides, the number of corners also increases accordingly. This one-to-one correspondence between sides and corners results in the same sequence for both. Question 2. Count the number of lines in each shape in the sequence of complete graphs. Which number sequence do you get? Can you explain why? So this is complete graphs. Answer: the sequence for number of lines 1, 3, 6, 10, 15. 1, 3, 6, 10, 15. This is the sequence of triangular numbers. The number of lines increases as the number of vertices increases, following this pattern. This happens because in a complete graph, every vertex is connected to every other vertex, leading to progressively more lines as new vertices are added. So friends, these red dots are called vertex, and in plural we called vertex as vertices. Question 3. How many little squares are there in each shape of the sequence of stacked squares? Which number sequence does this give? Can you explain why? So these are stacked squares. In the sequence of stacked squares, the number of little squares increases as we progress through the sequence. First shape 1 little square, this one. Second shape 2 multiplied by 2 is equals to 4 little squares, this one. Third shape 3 multiplied by 3 is equals to 9 little squares, this one. Fourth shape is equals to 4 multiplied by 4 is equal to 16 little squares, this one. Fifth shape 5 multiplied by 5 is equals to 25 little shapes, this one. Number sequence 1, 4, 9, 16, 25. This is the sequence of square numbers. It occurs because each step in the sequence forms a perfect square grid, with the number of little squares being equal to the square of the side length, that is n square, where n is the side length of the square. This pattern grows quadratically as we increase the size of the grid. Question 4. How many little triangles are there in each shape of the sequence of stacked triangles? Which number sequence does this give? Can you explain why? Hint. In each shape in the sequence, how many triangles are there in each row? So these are stacked triangles. Answer. In the sequence of stacked triangles, the number of little triangles increases with each step. First shape, 1 little triangle, this one. Second shape, 4 little triangles, this one, 1, 2, 3, 4. Third shape, 9 little triangles, 1, 2, 3, 4, 5, 6, 7, 8, 9. Fourth shape, 16 little triangles. Fifth shape, 25 little triangles. Number sequence 1, 4, 9, 16, 25. This is the sequence of square numbers. The reason this happens is that the stacked triangles are arranged in such a way that their structure forms a grid-like pattern similar to stacked squares. Each row of triangles builds on the previous one, leading to a quadratic increase in the total number of triangles as you move from one step to the next. This is similar to the logic behind stacked squares, where the side length squared gives the total number of small units, triangles or squares in each shape. Question 5. To get from one shape to the next shape in the cos snowflake sequence, one replaces each line segment by a speed bump. As one does this more and more times, the changes become tinier and tinier with very small line segments. How many total line segments are there in each shape of cos snowflake? What is the corresponding number sequence? The answer is 3, 12, 48, that is 3 times power of 4. This sequence is not shown in table 1. Answer. In the cos snowflake sequence, the number of line segments increases with each iteration. Here's how the progression works. First shape, equilateral triangle, this one. The initial triangle has 3 line segments. Second shape, each line segment is divided into 4 smaller segments, replacing the middle part of each segment with a bump, forming a star-like shape. Like this and this. Number of line segments is equal to 3 multiplied by 4 is equals to 12. Third shape, this one. Each of the 12 line segments is again divided into 4 smaller segments. Number of line segments is equals to 12 multiplied by 4 is equals to 48. So here are 48 line segments. Fourth shape, this one. Each of the 48 line segments is divided into 4 smaller segments. Number of line segments is equals to 48 multiplied by 4 is equals to 192. Fifth shape, each of the 192 line segments is divided into 4 smaller segments. Number of line segments is equals to 192 into 4 is equals to 768. So here are 768 line segments. The number of line segments follows a geometric progression 3, 12, 48, 192, 768. The pattern is multiplying the number of segments by 4 at each step, starting with 3 segments in the first iteration. This happens because each iteration divides every existing segment into 4 smaller segments, thus increasing the total number of segments exponentially. The end. So friends, we have completed all the question answers from this chapter. Kindly like the video and share it with your friends. Thank you for watching.